What is a power function? A power function is any function that can be written in this form. F of x equals ax to the b, where a is a constant and b is any exponent. Now, the many functions that we've looked at already are actually power functions. So something can be a power function and also have another name. For example, we have the square root function. The square root function is actually a power function because I can write it as f of x equals x to the 1/2 power. In this case, the constant in front of the function would be 1, so it would be 1 times x to the 1/2 power. Of course, another power function that we have is the quadratic function, the simple parent quadratic function. Now, if I added additional terms to it, like x squared plus 4x plus 3, it would no longer be a power function. A power function only has one term. Another example of a power function would be f of x is equal to 3x to the 1.6 power. So this exponent could be a decimal exponent. It doesn't have to be a whole number or fraction. It could be any kind of exponent. I could even have f of x is equal to 3x to the pi power, although we don't see that very often. That still is considered a power function. We can also have negative exponents. F of x is equal to 4x to the -3, for example. Now, that is the same thing as saying f of x is equal to 4 over x to the 3rd. So functions like the inverse variation function, f of x is equal to 1 over x, or what we call sometimes the parent of the rational functions, that can be written as f of x equals x to the -1, so it is also a power function. So there's some examples of power functions. Actually, I just thought of one more possibility, is the simple linear function, f of x is equal to x. We could think of that as x to the 1st. So technically it's a power function too, although since that's a linear function, we don't usually lump it in the same category with power functions, but it, I guess, could be considered a type of power function. Now I want to look at the characteristic graphs of power functions, now that we've looked at a few examples. There are 3 characteristic graphs, and I'm only going to look at them in quadrant 1, and I'll explain why. If I have an exponent, like if I have a power function that involves an even root, like a square root or a 4th root, it's not defined for negative values of x. There isn't anything in any quadrant except positive values of x anyway. So I'm not particularly interested in what would happen on the other side of the y-axis. Sometimes if I have an exponent that's kind of, that is not a nice number, particularly one like pi, it might do some really odd things when x is negative. So I'm not as interested in how it behaves when x is negative. I'm mostly interested in how it behaves when x is positive, and mostly interested in positive constants. Although we could see with a negative constant it would flip it upside down into quadrant 4, but I'm mostly interested in quadrant 1 with a power function. Because power function has to do with things varying directly or inversely, so we'll talk about that in a minute. So let's look at 3 possible categories of power functions. One possible category of function is that we have an exponent that is greater than 1. So b is greater than 1. So remember, our function is f of x is ax to the b. So when I'm talking about b, I'm talking about the exponent. So if b is greater than 1, for example, x squared, that would be an example. What would be the characteristic curve that we would associate with that? Well, it would be a curve that is concave up. So an example would be f of x equals x squared. But all of them would have the same characteristic curve. Some would curve higher, more steeply up, but they're all going to curve upward in this concave up. So I'm going to write concave up. Now, if the exponent b is still positive but less than 1, so 0 is less than b is less than 1, An example of that would be f of x is equal to the square root of x, or f of x is equal to x to the 1/2 power. So here would be an example of case number 2. That still starts at the origin because when x is 0, y is 0. But now it's going to curve downward. So this is going to be concave down. Notice that both of them go through the point 0, 0. So it includes the point at the origin, because if I plug in 0 for x and it's raised to an exponent, it's still going to be a times 0. If I plugged in 0 for x here, it's going to be 0. Now the third category is when b is less than 0. So an example of that would be y, or let me stick with my function notation. F of x is equal to x to the -1, which would be the same as 1 over x. So notice, with large values of x, I'm going to get small values of y, and with small values of x, I'm going to get large values of y, and x can't be 0. So what we're going to see is a graph that has the x and the y-axis both as asymptotes, and it just curves like that. So 3 possible cases. These are all power functions. The first 2 are known as direct variation. The last one is called inverse variation. And the reason why, when we say direct variation, we're saying as x increases, y increases. So we have a direct relationship between x and y. As x increases, y increases. In inverse, excuse me, in inverse variation, we're saying as x increases, no dash there, as x increases, y decreases. So we have an inverse relationship. That's why it's called inverse variation. Now I want to build on that a little bit more and talk about some of the phrases associated with power functions. Sometimes we'll say y varies directly with the square of x. Actually, let me stop and say, let's just start with y varies directly with x. Y varies directly with x means that we have this function, y, or f of x, equals some constant times x. Y varies directly with the square of x. So we're going to say y is equal to some constant times x squared. Notice that's just a power function. Those are power functions. That should not be in past tense. Y varies directly, and sometimes they use the word as instead of with, directly as the cube root of x. So we'd say y is equal to k times the cube root of x, or y is equal to kx to the 1/3. So that's a power function as well. Make that look more like an exponent. Now what about inversely? We could say y varies inversely with the square of x. So y equals k over x squared. So in other words, as x increases, y is decreasing. So I put the x squared at the bottom, but notice the constant still goes in the numerator. Or just y varies inversely with x. So y equals k over x. So all of those are types of power functions, inverse and direct variation. Those are phrases that are typically used in mathematics, so I wanted you to be familiar with what that means when you say y varies directly with or varies inversely with something. It just means you're either multiplying that relationship by a constant or taking a constant and dividing by that relationship. Okay. Those are some basics about power functions that you need to know in order to work with power functions.